light house today. I guess the Thanksgiving holidays have arrived. Yeah. I actually was thinking we didn't have class today for most of the semester, and then I realized it, so I had to cancel my trip to California so I can be here with you. But it's all for the better, so we have a little bit more time to deal with these giant planets, which are, I think, probably the most important pieces in this whole puzzle. Anyways, and we didn't make it. I know we're a bit behind with respect to the Moodle and everything, but hopefully that's not too disturbing. I think it's very important that we spend time on this, because honestly, after we finish up with the ice giants, hopefully we'll get through them today. That's about it, right? So we have these trans-Neptune objects like Pluto, which was a planet when I was a kid. It's not anymore, I guess. And there's a bunch of those sort of sub-planetary sized bodies. Problem is, of course, that the further we get away from ourselves, the less we know about these things. So most of the ice giants we're going to talk about today, we've maybe visited in close range once so far. They're so far away. It takes years to get out to them. And so we know very, very little about them. But they are really, really interesting players in the story. And my pen. And so hopefully we can conclude that idea. But the way that this whole narrative is shaping up is pointing, like I cracked open last time, towards a more evolutionary paradigm for the planet formation here. And so before I continue with that, and I'm going to tell a kind of interesting story about a paper that came out last year with regard to the super-Earths and why we don't have any, and really how they fit into this paradigm. Can we just review a little bit about what we talked about with gas giants? Can somebody maybe, let's just start out. Does somebody tell me something interesting they remember about the gas giants from last time so I can see where we're at? Yes? Yeah, the core is very difficult to understand about these things. I mean, partially because we haven't really gotten a lot of data, but also because it's buried beneath enormous, enormous layers. I mean, the cores of these giants are approximately the size of our own planet, but they're tiny compared to the radius of them, right? They're sort of dwarfed by these thick layers of condensed gas, which is really liquid. And so, it's very difficult to see what's going on at the interior. And the ideas range from something rocky like our own planet to something like a strange form of ice to something like liquid metallic hydrogen, which is a very strange phase of that element hydrogen that we have had varying success creating here on Earth. So it's in some sense entirely hypothetical. What else? Yeah.
Surprised with how many moons Jupiter had.
Jupiter's got a lot of moons.
The way they actually group up and orbit different directions.
Yeah, that's something that's really startling and doesn't quite fit into the stories so far. So some of the moons orbit the wrong direction, quite a few of them. Same's true for Saturn. Saturn's got really weird orbits, right? So in all these different directions, they're not in one plane like with the rest of, say, with our moon, right? It's essentially orbiting on the same plane as our rotation in the plane of, not quite with our rotation, but more in the plane of the ecliptic. But we don't see that so much as we move outward. And actually, when we start looking at these ice ones, they're even weirder because their spin axis is completely tilted. So that's very strange. And, I think I actually think it's really exciting because these are puzzles that need to be solved. And so you guys can expect to see, if any of you are science nerds and follow these astronomy headlines as they crop up, I think we'll see a lot of change in the development of the story with respect to where these things came from. But for me, when I look at these bizarre, when I look at moons that are going the wrong direction or in the wrong plane, I'm thinking these things were probably snatched up later than the ones that are more stabilized. it just seems logical that it takes a while to stabilize something, right? The things will tend towards resonance, and they will tend towards stability over time, assuming they're not, counter-selected or eliminated from the pool for whatever reason. And we'll talk about how that happens in a moment. But yeah, you can get some idea of the age of the sequence of these events, I think, and I think that will become increasingly prevalent in the way that we make this story of our solar system. Remember, the story that we were inherited as little as 20 years ago, before we started being able to see other exoplanetary systems, was essentially 300 years old, and it was based entirely on trying to make sense of how all of the planets formed exactly where they are, looking more or less exactly as they look today, which is, on its face, it seems a little preposterous, but that's all the people had to go on for all of those years, because they just didn't have access to seeing any other of these species out there, any of these other planets, right? So it's like, if all you had to study was one animal in isolation and you didn't have access to all the others, it'd be very difficult to come up with any kind of rational story for how it came to be that way. This is kind of understandable in some sense. What else? Anybody? Yeah.
I had a couple notes on how Jupiter kind of protects us from a bunch of asteroids that would hit us.
That's really important, yeah. Yeah, it's a kind of a great, so you got to keep in mind, Jupiter makes up most of the material in the solar system other than the sun. And to the extent that Jupiter doesn't even entirely orbit the sun, it orbits a point about, I think, 7% the radius of the sun outside of the sun, right? So they're kind of dancing around each other. And that means it has a huge gravitational influence on the rest of the bodies in the solar system, in particular, the asteroids that would, that periodically do cause us trouble. But it's certainly a lifesaver, and it snatches up a lot of those comets that come wandering into the interior solar system periodically. And it may also have a role in pulling those comets in too, so it could be the bringer of bad news and also the extinguisher of that same problem. So that's kind of cool. Otherwise, I mean, the main thing to remember, I think, with these gas giants, which aren't gas, but we'll call them that because that's the tradition, the main thing to remember is that their composition is extraordinarily similar to a star. And there's a fine line between those Jupiters and those brown dwarfs, which are on the edge of being stars and stars themselves. And of course, we haven't talked about stars at all in this, well, other than as sort of these apparitions we can measure the distance to using light, and we can get some spectroscopic information. We talked about that, but next semester, if anybody sticks around, we'll do stars with great luxury of detail, right? We'll really tear into them, and we'll start to see how really similar they are to these gas giants and brown dwarfs, except for the fact that they have more of that stuff crammed into a smaller space, and hence we get into this fusion business, which is where these atoms are actually sort of melt together under pressure and form new elements. And so it's a very, very fine line. I think that's what's so intriguing about these Jupiters and these gas giants. And really all these bodies, which seem to be on this continuum. And I think there's a good case to be made for some different evolutionary transitions that are potentially occurring amongst all of them. So, all right, if we don't have any more questions or points about the big giants, I want to move towards a discussion about the ice ones, because in some sense I think that they're a really, really interesting link between where we're sitting right now on this very interesting and unique planet and some of the more common ones, because most of the planets that we see in these other exosolar systems are these larger planets, and the ones that are, most of them, are, and that makes sense because it's easier to see things that are big. But most of the ones that are even sort of like Earth are huge compared to Earth. They're a bit smaller than Neptune, but they're way bigger than us. And so the question becomes, why don't we have any of those? Because they're the most common type of exoplanets in some sense. Another interesting fact about looking at all these exosolar systems is that they're very homogeneous. The planets in them seem to be all of the same type, and we don't have that, right? We have a lot of different types of planets. And that's really strange. So most of the exoplanetary systems, especially the young ones, have a lot of the same type of planet. And again, this to me points out like a selection process that's happening, that we might be in an older conformation of something that's been evolving and changing over the years. So how does that happen exactly? Well, the standard story, which you probably, you'll certainly get this from the textbook and so forth, is that these gas giants, like the ones we've been talking about last week, they sort of start off very similarly to the way that the standard model treats rocky planets, that there's this accretion of heavy things like these pebbles and so forth, that sort of swoop up gas in this disk as the solar system's forming. Now, there's serious trouble with that idea, as I've mentioned before, which is that it's very easy to get little grains of dust to stick together, but because they don't have much recoil, really. But once you get pebbles, it's really hard to get pebbles to stick together because they just bounce off one another. So there's this sort of intractable problem with this core accretion idea, which is how do you actually get a big chunk, a boulder-sized rock to fit together under gravitational pressure? It doesn't really seem to be possible. So you need other mechanisms to do that. You need to slow it down. And so, there's a great deal of effort going into trying to rescue this core accretion idea. But the standard model for the gas giant formation in all of the planets is that it does somehow happen that these heavy things accrete, and that once they accrete, they have sufficient mass to be able to start to accumulate gases and so forth. Now, I'm a little bit troubled by that. I think a lot of people are, but and I think that a more evolutionary approach can save some of those ideas, because if you think about it, once you have a big ball of gas of some sort, it's actually quite easy. It's quite heavy, and it has the ability to start to grab up things that are pebble-sized and squish them down at its center, right? And you can actually imagine the circumstances by which you could let's say, compress a core, right? And so I don't think that we should take it as any accident that the interior of these giants, in particular the ices and so forth, have cores that very much approximate the rocky planets themselves. And so the question is, by what means could you arrive at something like that over evolution, over long evolutionary timescales? So the idea with the icy planets is, the icy giants, let's say, is they're really not that different from the gas giants in composition, except they have a few more heavier elements, right? So, and we'll talk more about their composition, but let's say they have more complex molecules in them. They're heavier. And they are very cold in order to form these, because a lot of the heavy chemical reactions form through condensation, essentially, right? It's sort of like how dew falls out of the atmosphere, right? Well, there's some problem with this, because in order to form those, you need to have them form at a pretty far distance from the sun, right, in order to condense these cold clouds of material. But the central problem with that is that beyond, let's say, 20 or 30 astronomical units where we would expect these things to be forming, they basically run into the problem that their velocity out there with the masses that would be necessary that we see would essentially send them flying off into space. And so there's a bit of a trouble with how do we form these things where it's cold enough, but close enough so that they don't fly away. It's a very perplexing idea. And again, I think that there's reason to open our minds up to the fact that, well, maybe they didn't start off looking exactly like ice giants. Maybe they started off with something much more simple, and they got cold, and they cooled, and they were able to condense a lot of these materials out of those eventually over time. And once we look at the composition of these, I think that'll make a bit more sense. So, and all of this also, I think, is buffered by the idea that we see a lot of these giant planets in exosolar systems getting cooked off, right? Their atmospheres, they're very close. They're much closer than we would have imagined Jupiter to have been during its formation in this old 300-year-old model. They're very close, and their atmospheres are getting stripped away from them in many cases. So at the very least, you have a lot of thermal flux, you have a lot of energy exchange going on, you have the potential for complex chemistry as a result of that, but you also have just a great loss of material. So you have a lot of opportunities for transformation of these bodies, which is really, really fascinating. And again, this information is just so new. It's really within the last decade. First exoplanet I think was in the 90s that we saw, but most of these surveys, I think we have about 5,000 or so exoplanets detected at this point, most of those within the last 10 years, 5 years even. So it's just brand new information. It just hasn't really been slotted in properly to the overall narrative that we're telling. And I think that's what makes it really exciting, actually. Now, what do I want to say about these? So, a lot of people are again trying to work off of this core accretion model. They're like, well, we're not going to worry about the pebble boulder problem too much. Let's just assume it happens. So how do you produce these planets? Well, you have to have them migrate a bit, right? They have to move from warm zones to cool zones. They have to change places a lot. I think that's totally reasonable. The question is, are they starting as pebbles, or do they end up as, or are they starting off as rocky cores, or do they end up as rocky cores? That's the really interesting crux as far as I can see it. All right, so this is the paper that came out last year I wanted to talk to you about. So this most recent exoplanet survey, Kepler, well, I guess Kepler was the first one, I'm sorry. I believe TESS is the new one. But anyways, this Kepler probe found something quite interesting, which was that there was a lot of planets between the radius of Earth and Neptune. But the way that it was distributed was such that there was this interesting value that appeared between in the size of the planets. So you can see on this chart here, we have planet size with respect to Earth. So, 1 Earth radii and so forth. I think we can't detect the Earth-sized ones because they're just too small, is probably the truth of it. But we can detect ones that are a bit bigger than Earth quite easily. And what's very strange is that they have this bimodal appearance. So there's basically two different populations that appear, and there's nothing in the middle there. So you see these things which, this second peak to the right would be essentially the super Earths, right? And then things that are approaching the Earth are below that, and there's nothing in between, which is really, really interesting. And so the question becomes, why is that? And the conclusion that the authors come to is complicated, but there's two main factors that they think about. One is that when you have those planets in that range, they set up these simulations, and what happens is they tend to be in quite unstable orbits, and they tend to crash into one another. And when we think about a lot of the debris, so we have this asteroid belt, right? Which we'll deal with, I think, the next class that we have. Well, we'll get to it in the next topic anyways. What is this, right? Why is all of this? The standard story is that it's leftover from the formation of the solar system, but is it? Or is it leftover pieces from something more catastrophic that happened in the past? So, and the other idea is that these planets, these large planets, say super-Earth planets, have a tendency to be pulled in close toward the sun, where they undergo this photoevaporation as well, which cuts them down in size, right? Strips off their atmosphere and gets them cooked down to something that looks a little bit more in the Earth size range. Now, this paper came out last year, right? So this is absolutely brand new. I would not be surprised if these ideas that I'm putting on the table for you are going to show up in the textbook next year. It's one of the cool things about the textbook that we have is that it updates in real time. And I remember when I was reading the textbook last year and making some of the slides up, sometimes the paragraphs would change while I was reading them, right? It's that much on the move, which is really the way science should be. I think it's really wonderful. I mean, when I was in college, it was all paper textbooks, and what was written was honestly probably 10 years behind the curve of what people actually thought. And so this is one of the really cool revolutions of having this kind of online textbook, is that we can really stay up to date on what's happening. So yeah, we'll see if this this way of thinking makes its way into the textbook next year, but so far not so much. So, actually, I think I misspoke about something. So let me go back to this slide. So this first mode, the first hump is what we consider super Earths. The next hump is what we call mini Neptunes, actually. So I think I misspoke about that. Now, the interesting thing is that the composition is not too different between the two. So these mini Neptunes have a mass between they start off having this mass between 1 and, oops, I'm going to go back to that slide. They have a mass that's pretty large. After they undergo this collision, these collisions and photoevaporation processes, they result in these what we'd call super Earths. And I believe that these solar systems do have Earth-sized planets too, that we're just not able to see them. What else do I want to say about these? All right, so let's look at what happens during these photoevaporation processes. So what's really interesting is that what you have in these rocky planets is that a lot of the basic components of rocky planets versus, say, the mini Neptunes are essentially identical. It's just the ratios of the composition which are differing, right? So as you start to cook off the outer atmosphere, which is this hydrogen layer, right? And we see this as well on these icy planets too. They're just like Jupiter and Saturn. They have a hydrogen atmosphere, but it's much thinner than it is on Jupiter and Saturn, right? So you can imagine that if they were close to the star, that's the first thing they're going to lose. It's the lightest elements that they have, right? They're also going to some different chemical reactions are going to occur which might enrich the water. And then just by virtue of having lost so much atmosphere, they're going to have a larger proportion of rock as a result of it. So this is really, really intriguing. The fact, yeah. Yeah, exactly. Yeah, so I guess what this comes down to is we don't really know the mechanism of it, but some combination of collisions due to the instability in that size range and photoevaporation is thought to perhaps account for the transition between the two, which results in these two different populations that are very distinct. One that's essentially finished off and sort of cooked down, and one that's still volatile and large, these mini Neptunes. Now it's interesting, we don't have any mini Neptunes either in our planetary system. And nobody really knows why that is. One possibility is that they've already evolved out of being mini Neptunes into something being like, well, the thing that we're sitting on right now, right? Again, not a popular perspective, but it's logically consistent at least. Problem is the timescales, again, are very, we like to treat everything, science in general likes to treat everything as a gradual process that happens in a very predictable fashion. This is a really safe, conservative perspective, a way of looking at things that's reassuring. But I think what we're coming to realize is that things happen very quickly sometimes, right? If a planet is, say if we took Neptune and stuck it right next to the sun, things would change very quickly. And it appears that at least in other solar systems, this kind of thing happens. Or we don't see it happen, but we see these planets in the wrong location, let's say. There's no way a Neptune could have formed right next to a sun, but we see them there all of a sudden. We see Jupiters, they couldn't have formed right next to the sun, but they're there, and they're being changed rapidly. We can see them literally dissipating as they're there. So, we have this sort of unsettling feeling that things happen very suddenly sometimes. And if we allow that possibility into our hypotheses for the solar system itself, then we're really considering some pretty drastic evolution of these bodies over time. And again, I like the idea of the evolution of the Neptune into something like the super Earth, into something like the Earth, into something like the rocky planets, because it doesn't have these wild contradictions of how do you glue things as dense. Remember, we're sitting on the most dense body in the solar system. How do you do that by just squishing pebbles together under their own gravity. It really, really strains the imagination and strains the mathematics to make that happen. It's a hard pill to swallow. But if you have a huge planet full of really dense, like these really, really crushed down dense molecules, they can be simple like Jupiter, or they can be more complex like the ice giants. That's a lot of material and a lot of compression on the core, right? And you can imagine something like that squishing pebbles together. And I think that's a really intriguing possibility for how we end up with something as dense as that which we're standing on today. And so we'll see how this plays out in the future. Anybody have any questions about that before we take a closer look at these two? All right. Again, I'm not saying this is the case for sure. I'm saying it's intriguing, though. So, all right. So when we say ices, it's not exactly what we mean, okay? So when we think of ice on Earth, we think of something that's really, really cold. Now, a lot of these ices are okay, so you can actually create forms of ice in water on Earth using different methods besides freezing it. And this is maybe a surprise to you, but ice that's under water that's under extraordinary pressures, ice that's under extraordinary tensions, can actually form when water is at, let's say, less than freezing temperatures. This is very perplexing, but you got to think, all that ice really is a solid form of some otherwise volatile liquid, right? So if you immobilize it in other ways besides taking the wiggle out of the molecules, which is what heat really is, then you can also get something that it forms a solid. And I think that's closer to what we're thinking of when we're thinking of the bodies of these things. So they are icy-like, but those ices are not entirely due to the volatility of them due to temperature alone. Because as we'll see, there's quite a good deal of heat residing in these large icy bodies, right? All right. So here's the basic orbital plan. Uranus, very, very far out there. We'll talk about Uranus, Neptune also, although Neptune's not showing up in this. I think Neptune's orbit is, oh, there it is. It's creeping around the side very slowly. So these things orbit extremely slowly, right, on the order of hundreds of years, which is quite fascinating. It makes them, it makes getting a good view of them, well, it depends more on our orbit than on theirs, right? So every year we're going to have a particularly good window to view these. And honestly, Uranus, Neptune, you can see. Uranus, I guess, is technically able to be seen with the naked eye with a telescope. I've never seen it before, although I heard it was visible last week. But it's very, very dim. In fact, you might recall there was some talk of some of these planets having been, one or the other, I can't recall which it was, having been detected because of the fact that the other planets were perturbed. And so the astronomers sort of knew where it should be before they were able to actually find it. And then once they figured out that there should be a planet there, they actually went and looked for it and found it quite quickly. So they're very difficult to see. They're extremely far away. We'll get back to these in a second. So let's take a look at the composition of these things a bit. Actually, can't even read it on my screen. So more simple compounds in the Jupiters and Saturns, right? But in a sense, we also have some of those same volatiles on the outer layer, some of those very simple molecules, hydrogen, helium, methane gas. Methane, that's interesting. So methane is just a carbon with 4 hydrogens stuck on it. So we have carbon, which is interesting. That's a very useful molecule. It articulates in 4 points, so it forms this nice little tetrahedron with hydrogens. Then there's thought to be the accumulation of more rocky silicate type things, right? This is the mantle. We see more complex chemicals, water, ammonia. Now, ammonia is basically just like methane, except it's got a nitrogen at the center. And nitrogen's a heavier element, of course. oxygen required for the water. So these things have snatched up bigger elements over their evolutionary histories. Now, is that because they started off maybe more something like this, and then as they lived, they were able to pull in some of those heavier compounds from the rest of the solar system over the years, and then eventually concentrate them? Maybe they lost their outer layers through photoevaporation of different sorts. I don't know. I don't know if anyone knows, but it's very difficult to form one of these things exactly where it lives today. That seems to be an impossibility. So they need to have had some sort of wandering history for this to have happened. And it's not even clear why exactly, had these things all formed in the same place at the same time, why some of them would have snatched up all of the heavy elements and some of them wouldn't have. Particularly since these things are smaller than Jupiter and Saturn, right? They're less massive. They have less gravitational pull than Jupiter. So how is it that they grabbed up all of the heavy stuff? It's a very perplexing question, right? Unless as I keep hammering on that perhaps they're actually representing some stages in a similar evolution, right? All right. Let's see, what else can we say about these things? Yeah, well, again, this gives you a sense of the layering structure. So there's this, below this outer gassy layer, which is quite thin compared to Jupiter and Saturn, we have this liquid hydrogen, liquid helium, right? It's under a great deal of pressure. So those simple atoms, hydrogen and helium, they sort of exist under such compression that they behave liquidly. Now, water, when it's compressed that much, actually, like I said, begins to behave in a very, almost like an ice in some sense. Now, that's these concepts of phase really start to fall apart under extreme conditions. It's very hard to imagine. When we hear about something like a liquid hydrogen, liquid metallic hydrogen, or a pressurized ice, what we're really talking about is that at some point you crush those things together so tight that they actually sort of behave as if they're one, right? The atoms actually, they're not fused into single new elements, but they actually have these delocalized electrons. They're in some sense plasmatic in that way. They're able to act as one unit altogether. So we have very strange forms of matter as we get closer and closer to the core. And then, of course, the thought is that there's a rocky core at the center of these, which very much, it's actually about the exact same size as our Earth, right? And very similar density, very similar composition. I don't think that I would get in trouble for saying there's essentially an Earth buried at the center of these things, which, it may be a complete coincidence, but it might make a lot of sense also. So another really interesting thing about these ice giants, their spin axes and their magnetic axes are very perplexing. So if we look at Uranus, it's spinning almost in plane with the ecliptic. This is its rotational axis, right? This is really, really weird, actually. It's quite unique among the planets. Neptune's a little bit more in line, but both of them, their magnetic axes are completely off from their spin axes. So why is that? Well, nobody really knows, especially considering the theory that we have for how our magnetic fields are generated here and on Jupiter, which is more or less similar to the way in terms of the rotational dynamics leading to these convection cells and the production of these almost solenoid-like dynamics inside of the interior that lead to magnetism, right? But it doesn't work out so nicely on these ice giants because, well, their magnetic axes have very little correlation with their spin axes. So something else must be going on. And the theories for those they leave a lot wanting. But the thought is that there might be more shallow currents in those volatile ices and so forth there's a lot of friction in the shallow levels that lead to the production of electrically active species, and those in some sense are able to create, by interacting with the sun to some extent in the solar wind, to create these magnetic fields. But it's a bit unsatisfying. I think it's an open topic still because they're quite strong. Let me see here. So Uranus and Neptune have magnetic fields that are 50 and 25 times the strength of the Earth's, for instance, right? So these are not just simple induced magnetic fields like something, we talked about some very, very weak magnetic fields like Mercury, for instance, right? These are not simple, weak fields. These are very, very strong. And so the mechanism is still out there. There's a lot of work to be done on that. All right, and then of course, there may be some clues in that strange form of ice that we were talking about, right? That superionic ice, which I don't know that ice is the right word, but there's some strange state of these matter, these molecules like water and ammonia. They behave very strange under pressures, and the pressures that they're producing inside of these interiors is far beyond that we can achieve stably in a laboratory here on Earth. Right? It's just an inconceivable amount of material squishing down on itself. And so something strange happens. Next semester, we'll pick apart the idea of plasma a bit more. I think we've touched on it a little bit in this class, but that word it's not quite a meaningless word, but it's almost meaningless because it covers such a wide range of interactions, right? You're essentially saying that material under extraordinary pressures or temperatures can behave as if it is metallic in some sense, as if it's conductive, it takes on new properties. And so if something like that's happening with the molecules, like the ices inside of it, then perhaps we have the opportunity for new magnetic processes as well, because electricity and magnetism are essentially two sides of the same coin. So we'll see what happens with that in the future. All right, we'll check out Uranus first. So Uranus is the 7th planet from the Sun, and it's actually it has the coldest atmosphere of anybody, which is about minus 371 degrees Fahrenheit. So you wouldn't last a second in its atmosphere. These things, again, until you get down to the core, they don't really have a solid surface in the sense. So, and if you were standing on the core, well, you'd be crushed to smithereens by the pressure. So, it's actually one of the only places I can think of in the universe, well, aside from maybe the interior of a star, that has that much pressure. It really seems to have the pressure to be able to squish rocks together and melt them. We have some of that under our feet right now, but this is going to be, way, way more pressure than that under our feet because these things are so much more massive than the Earth. All right. By the way, this myth is kind of interesting. So the name Uranus, where does that come from? Do we have any myth people in here? Anybody in the classics department or anything like that? You guys have a classics department? I don't know. Maybe humanities people? All right, so Uranus was this Greek god of the sky. And this isn't, I'm going to pick on the Greek tradition just because it's the one that I have the most access to. I can't speak a lot of, I can't read the texts from the East as well. But it is interesting, before I even launch into this, that the Greek god of the sky, Uranus, okay. In Chinese, Japanese, and Korean, this same star is treated as the sky king, right? Let's say, the same thing appears in Mongolian. It's called the king of the sky, the ruler of the heavens. So this seems to be, for whatever reason, a universal idea, right? That this planet, it wasn't an observed planet at the time, but this deity that the Greeks and Romans used to associate, which we eventually picked up to use for the name of this planet, was the ruler of the sky. Now, the Greek tradition is kind of disturbing. In the myth of Uranus, Uranus's son was Saturn, which they called Cronus, right? So Saturn represents time, essentially. And Saturn actually castrates his father, so he cuts his genitals off and casts them onto the sea, which then spawns Venus. And it's like, that's a really, really interesting myth to try to unpack. Like, what is going on there? And I think that there's something quite profound about the idea of time being let's say, that which orders things for the human experience. I mean, most people would have a hard time even defining what time is, but we all have a sense that once we invented that idea of time, right, other than just experiencing the passing of events, but once we were able to start thinking about time, like what's going to happen later today. In fact, all of your lives, I'm sure, from the time you wake up to the time you go to bed, are in some sense ordered in terms of the past and present and future. You're thinking about what do you have to get done for tomorrow? What do I got to do today when I wake up, right? And so there's something about taking this idea when Saturn castrates his father, who's the Sky King, right? Where there's this idea, and then of course spawns Venus as a result of this. And Venus, of course, represents in many of these mythologies this idea of passion, right? And something very tortuous in some sense, something very very emotional, very fundamental to the human experience. And there's something about that, it's hard to see anything approaching, let's say, in animals, right? You do see things like, you obviously have reproduction in animals, you have pairing and bonding of animals in some sense, but it's taken to a whole new level with animals, with this whole concept of romance and courting and these lifelong partnerships that many people develop. It's very unique, and there's something about the planning ahead for that with regards to time that occurs in this transition. And I think what these myths are, in some sense are remembering this moment where humans were in some sense occurred for the first time, right? When they were for the first time able to use language in order to wield these concepts, right? In order to communicate them to one another. In a sense, when humans first woke up, right, from being like all of the other animals and were able to start to order their lives. I think the invention of time was critical to that. I think this realization that, hey, I've got to take care of myself in the future, not just myself right now. And how that spawned the different passions, right, including Venus and so forth. I think there's some very, very profound memory embedded in that story. And so, of course, when we discovered Uranus, and Uranus was the one that was discovered mathematically, right? When we did that, we gave it the name because for whatever reason, it was that important to us, right? It seemed like an important story. And I think that, people do these things kind of subconsciously. They think, oh, well, that's an important myth to the ancestors. We should probably preserve it. And so they name the planets after it. But I think that it's preserved for a very subconscious and important reason, because in some sense, I think we're remembering those distant events when we became humans for the first time. Which, if you ask the archaeologists when that happened, it's like the dates range, but it's not that long ago, right? It's like maybe 50,000 years ago, maybe 150,000 years ago, but like pretty much not that long ago. When you think like basically we were anatomically modern, we had our bodies, right, more or less the same, maybe 1 million years ago. So 10 times as long. And then all of a sudden something happened, right? Something really, truly profound happened. And people began to organize, right? They began to make order out of the chaos of existence and try to actually plan and think about their past with respect to their future and how they could do things better. And that's the fundamental human story, and that's the one that you see in every single mythology around the globe, from the indigenous tribes to the Bible, right? It's this idea that all of a sudden we had this awakening from, this almost paradisical existence of ignorance, where we don't have knowledge of what's going on. And then all of a sudden we do. And that's, both incredible and it's also very painful, because it awakens all of the pluses and minuses, right? I mean, every single wonderful experience in your life has the flip side of it too, right? It's like realizing that you can plan your future is wonderful, and you can make yourself into something new and better than you were yesterday is amazing. But it also comes with the realization that you're going to die eventually, which is, almost impossible to reckon with, right? The same with love, right? You might find like this perfect partner, and it might be the greatest thing that ever happens to you. But again, it comes with the difficulty of sustaining that kind of relationship over the years. It comes with the difficulty of death itself, right? You know, everybody that you love is going to die. That's a really difficult thing to wrestle with. And so I think a lot of these mythologies try to wrestle with those concepts and place, you know, show how they can still be meaningful despite the tragedies that inevitably underpin them. All right, back to the rocks. Okay, so like I said, these things have been investigated very, very little up close. So NASA made a flyby of Uranus in 1986. This is the only time that we've ever been to this planet, okay? And there's some talk on the books right now, let's see, that we might launch something in 2031 to get back out there. I don't know. I don't think NASA's committed any money to that right now. So all of our information comes essentially, all of our up-close information comes from that one probe that went by, which, let's see, how close did it get? It came within 81,000 kilometers of the cloud tops, which, you know, isn't that close to begin with, but it did have a chance to go and check out some of the moons, and I think that it got some pretty interesting readouts about the weather patterns, and we got a lot of that magnetic tilt information from that flyby. Basically everything that I told you so far is from that one mission. So, I don't know. All of this, I think, makes, this fact, let's say, lends a great deal of redemption to the idea that we don't have a very coherent picture of how these things formed and what their fate ultimately is, because quite honestly, we're just in the very infancy of understanding them in an up-close fashion. Unfortunately, I don't have the numbers for you, but I know that it takes many years to get there, and communication's even worse, right? It's like, you know, I think communicating with Mars, the round trip is something like 15 minutes at times, depending on where it is in its orbit. And so it's going to be on a matter of hours in order to communicate with, if you even are managed to send like a remote control probe out there, it's going to be very difficult to drive it, right? Because you have hours of delay in your signal, right? Just in terms of light minutes that it takes to get that signal out there. So this is really tricky, and I think this is what NASA is struggling with in terms of how to explore these things, because on one hand, that's, you know, you can maybe program some things ahead of time that you want. You can take readings and beam them back. But in terms of actually controlling probes on the moons out there, driving things around, it's nearly impossible. And I mean, the only thing you can think of is you send people out there to drive the probes around, or to at least be able to remain in close contact with the remote control devices. But then you have people stranded years away from the Earth, right? If anything goes wrong, there's little hope that you're going to be able to help them out. So it's a complex problem of how we even go about adequately exploring these in the future. And I don't think that anybody's worked that out yet, nor is it particularly, let's say, a high priority, because, of course, the priority is getting the space exploration infrastructure put together. And so the moon makes the most sense for that. Some people think Mars is a good place for that, but at any rate, the closer bodies make a lot more sense. All right. So, like I said, it's going very slowly. You know, the further you are away from the sun, the less tug that you get, right? So you're gonna be pulled around the sun much slower. This thing, Uranus, takes 84 years to make its way around the sun. It's going to be completing its third orbit around the sun since it was first discovered in the late 1700s right now. So it's also, another interesting thing about it is that Uranus has, I think, the highest eccentricity in the whole solar system. So it's the difference between its most narrow point, right? So it has this long elliptical orbit. And the difference is actually 1.8 astronomical units between the length and the width of that orbital path. So that's 1.8 times the distance between us and the sun. That's how sort of compressed this ellipse is. That's really interesting. And we don't, again, why is that, right? Why has it become the case? How is it still stable? Well, in some sense, inevitably involves the fact that it's in resonance with all of these other planets, right? It's getting tugged in just the right way. So were there other planets similar to Uranus that had, even worse eccentricities? We wouldn't know because they're not here anymore, right? At some point, your forward velocity is just no match for gravity, and you're gone, right? So we're only left studying what we can see that remains from this entire pageant that played out in the deep past. It's very dark with regard to sunlight out there, right? So it gets about a 400th of the intensity of light that we receive here on the Earth. But it does produce a fair amount of its own heat, and we'll talk about that in just a second. I already talked about its tilt. Now, what's kind of interesting is that because of the fact that it's tilted, each pole gets something like 42 years of continuous sunlight, right? Because in some sense, it has that same idea that we have of the seasons, but it's tilted at a much greater angle, right? And so as it goes around the sun, it's going to receive new light depending on where it is in that progress. And instead of it being a sort of day-night thing, right, it's rotating on its side. And so the poles continue to get continuous. The poles are almost like the day, or let's say the seasons are almost like the days, right? Because of this sideways rotation, which is quite interesting. All right, so there it is next to the Earth. Quite a behemoth. It's about 14.5 times the mass of the Earth, which actually makes it the least massive of all these giant planets that we're talking about. But its diameter is larger than Neptune's, so that actually results in it being quite a bit less dense on average. So most of the material in this thing is in the core. So its average density is only 1.27 grams per centimeter cubed, whereas ours on Earth is somewhere in the neighborhood of 5, right? Because we are basically all core. I think that's a reasonable way to think about it. Of course, we have a layered structure as well, and we have our own core proper, but in terms of the composition, the majority of that material is squished into the center of this thing, into something approximating the size of the Earth itself. Uranus does have internal heat. This is what I wanted to talk about. It has less internal heat than Neptune, right? So Neptune actually gives off about 2.5 times more radiation than it receives from the sun. Let's see here. Uranus is pretty much on balance, right? So it radiates about the same amount that it receives from the sun. It's essentially in equilibrium in that sense. So, this again, for me, points to it being a little bit more evolved, it having had cooled for a bit longer. It seems it's smaller, it's lost more material than Neptune. It's less dense, right? There's the possibility of these two being on a continuum, which might make more sense when we look at Neptune next. All right. I don't have too much to say about that. Oh, we haven't talked on this yet. So why is the thing blue? That's a good question, I guess. It turns out the blueness actually has to do with the methane in the upper atmosphere that's absorbing. So methane has prominent absorption bands, right? Those molecules are able to vibrate really harmoniously with visible light in the blue spectrum, which gives it this kind of aquamarine or cyan color. Gosh, there's so little known about this thing. Along with methane, we did on this Voyager mission, we did detect the presence of some other more complex compounds. So some of those include ethane, acetylene, methyl acetylene, and diacetylene. These are basically strings of carbon with hydrogen attached to them that are slightly more complex than methane. And so again, this points to me to having been subject to a lot more cooling, right? More condensation, and time, right? It's almost like it's older in some sense than the others that are these simpler compounds. There's also traces of, in the atmosphere, there's traces of water vapor, carbon monoxide, carbon dioxide. And, the traditional thought is that those came from elsewhere. Maybe they were deposited by comets or something. But if you'll recall the hypothesis that all of our water came from comets, that hypothesis is sort of dying a quiet death in the background right now. So I'm skeptical of that, and I would look more towards chemical evolutionary processes that I think will probably prevail in the future. Now, Uranus has a number of moons itself, and we have time to look at these individually later. So the 5 main moons, the big ones, called Miranda, Ariel, Umbriel, Titiana, and Oberon. These are the smallest, in terms of the large planets, these are large moons. These are the smallest among the different giant planets. So the mass of all of these moons put together would still be less than the biggest moon of Neptune. All right? But let's not worry about those too much because we have a whole lecture set aside for moons, and we'll explore the differences and commonalities of those later. It has a ring structure, which is quite interesting. And again, we'll have a whole lecture devoted towards ring structures. Ring structures, just to touch on it briefly, it's unclear in some sense whether ring structures are a precursor to moon formation or whether they come as a later part, right? If the let's say, dissipation of moons, the destruction of moons leads to ring systems. And some of the latest, let's say, theoretical work on the ring structure of Saturn points to it actually being created by the destruction of a moon. But, at the same time, there's little tiny moonlets embedded in that ring structure that could potentially turn into full proper moons at some point. So there might be a back and forth interplay in terms of these. And Uranus has a similar ring structure, although it's much thinner and more difficult to see in the optical range. All right, Neptune. So Neptune, one planet further out. It's the 8th planet from the sun. It's the farthest known planet that we have since Pluto got kicked out of the club. It's the 4th largest planet by diameter, the 3rd most massive planet, and it's the densest gas giant, which is really, really interesting. The density probably has to do with the fact that it's got these bigger compounds, right? So unlike something like Jupiter or Saturn, it has more of these complex chemicals, and so more material crammed into a smaller space. Again, also, both of these ice giants, their mass, their density in some sense could be accounted for largely by the ratio of the size of their core to the rest of them, right? The core is not, it is small, but it's not that small compared to, say, the core with respect to the body of Jupiter or Saturn, right? Where the body dominates. And the body is these simple elements, and therefore you have a less dense planet at the end of the day. Neptune's named for the god of the sea, which makes sense. It's blue. I think that's probably the extent of it. So Galileo actually made some of the first observations of this thing back in 1612. He actually thought it was a fixed star because he didn't, these things move so slowly, on the order of decades upon decades, right? So he was wrong about that, but he did seem to note that it was there. You can't see Neptune without a telescope, which is a bit disappointing. Although if you find one of those sky trackers, you might be able to track it down with a telescope. What else do I want to say about these? Again, we do name these things after the Greek gods, But it's not really a Western bias at all because, again, in every single one of these cultures, there is a corresponding god, right, of the sea. It makes sense, right? You're trying to essentially personify the experiences that you have, and everybody has experiences with the sea. So in Mongolian, it has the same connotation as the ruler of the sea. Hebrew, it's associated with biblical sea monster. Where else? Nawal, it's named after a rain god, so storms in the sea kind of being associated, still the watery god. Very similar stories that people tell. Everywhere, basically. So again, Voyager 2 is the only one that's ever made it out there to Neptune. This was in the 25th of August, 1989. This is Voyager 1 was actually thinking about going to it, but it didn't. It ended up going and seeing the moons instead. Particularly, this is it was able to go and check out the moons of Saturn. It would have taken something like 20 more years to make it over to Neptune, so it didn't. And this is a nice picture of that Saturnian moon, which we'll talk about, Titan. All right. So it takes 164, well, almost 165 years for this thing to go around the solar system. Again, further out, slower you go, right? It's basically orbiting in the ecliptic. It's angled about a degree and a half away from the axis of orbit of the Earth, let's say. Has a tilt which is pretty severe, but not nearly as severe as Uranus. It's tilted, I think, let's see, 28 degrees, 28.3 degrees. Remember, the Earth is on the order of 24 degrees, so not too different, which means that it's going to experience seasons much like us. But unlike us, each one of those seasons is going to last something like 40 years, right? What's that? Yeah, that's a very long, well, yeah, if you could grow anything there. Very long winter, too. All right, so, the composition, it's not tremendously different from Uranus, which we've already talked about. I don't think I'll bore you with that, but let's say it has an atmosphere which is very comparable to the other gas giants, right? This hydrogen, helium atmosphere. There's some traces of methane and so forth. The methane gives it that nice blue. What's really interesting is because of this seasonality, it does have the production of really extreme weather patterns, right? It has these storms. You can see a few of them here. This one looks a lot like the one on Jupiter, actually, at the bottom, this eyeball-looking storm. Of course, weather is driven primarily by convection, right, occurring in the upper layers. The different areas are getting heated differently than others, differential heating, and you get the rise and flow of currents of gases in those atmospheres, and you develop these storm systems. There's a close-up of that thing, the great dark spot. Now, these storms will probably be not as long-lived as the storms on Jupiter, right? Because there's not as much material tied up in them as there would be on Jupiter. Although that Jupiter storm seems to be dissipating, I think it's closed down quite a bit in my own lifetime compared to what it started as. And I remember when I was a kid, people were saying that storm would last for 1 million years or something. It doesn't appear to be the case. So these things are transient to some extent. All right, let's look at its layered structure a little bit. So we have a very similar pattern of layout to Uranus. Actually, it's almost, look at the typo on this chart, liquid. It's pretty funny. I don't know where I pulled this from. Hopefully not your textbook. What's interesting and what's unique? There's a lot more heat in this thing, right? So whereas Uranus and the sun are essentially on balance with respect to the amount of energy that it takes in and that which gives away, Saturn gives out about 2.5 times as much energy as it gets from the sun. And so I said Saturn, I meant Neptune. Now, why is that? Well, there's a lot of contradictory ideas about that. I mean, one is that there's just more heat left over from the formation of the planet itself. That in some sense was better insulated and kept this heat. I'm not sure. I wonder if in some sense its density contributes to this, right? So, you know, when you squish something like in a piston, you actually can make a good deal of heat occur, right? This is essentially how diesel engines work, sparkless engines. You squish stuff and they get hot. And I think there might be something very similar going on to that inside of this thing as well. All right. I don't know if I have much more to say about these two ice giants. I think that the really interesting point was really that which I gave at the beginning. I think that the next thing that we want to get to is to talk about the moons, and I think they kind of deserve their own attention. You know, I think the really exciting thing here is that, you know, and this is probably the last time that I'll bang on this before we move on and talk about moons and talk about comets, talk about asteroids and so forth. I think that it's really, really, really exciting that we have all of this information from other solar systems to start to fold into our models of where our own planets came from. And instead of trying to think of ourselves in isolation, right? Instead of just looking at one animal in the zoo, we have the ability to look at all the animals, not all, but let's say thousands of them, right? And we can start to think about the different processes and environments that tune them over the years into looking the way that they do. And so what I see is very simple conglomerations of material in stars, right? They're very simple in some sense. They're basically just hydrogen and helium, and there's a lot of it there. And so it undergoes different fusion reactions and different chemistries, and it produces all the different elements that we see, right? Each of the different atoms on the periodic table, which is behind this screen. They're all essentially fused in the star, but it's a very simple starting place, right? It's these clouds of gas. There's so much of it in one place that they're actually able to start to organize themselves into a ball, right? And as we move away from stars and we get into brown dwarfs and then we get into Jupiters, we have the appearance of more layered structures, right? The things start to cool off a little bit. There's condensation that begins to appear. And maybe as we go even further down that path, we get something that looks like these Neptunes, right? These large, or Uranus actually would probably be an even greater example, right? These more complex chemicals start to appear. There's interactions between those different atoms, right? The oxygens react with the hydrogens. You get water. You get carbons interacting with hydrogens. You get methanes and longer chains, right? And as that progresses even more, you know, maybe these Neptunes become, they sort of dissipate over time. They get too close to the star and they cook off layers and they become these mini Neptunes. And the mini Neptunes maybe get cooked off or they undergo collisions and you end up with things that look more rocky like what we're sitting on today, right? And so what we have here is this appearance of the idea of evolution in astronomy for the first time. I think it's hard maybe for you to appreciate it, but it's very possible that we're observing this moment right now is actually something that people will be talking about for centuries to come, just as the way that we have this extraordinary reverence for Darwin's ideas of evolution, and they're essentially taken as, you know, a foregone conclusion in biology at this point. And I think we're right on the cusp of a similar revolution in astronomy, and I'm glad to share that with you guys. But we'll have to wait and see how it pans out over the next few years. So I guess I'm going to stop here and let you guys go a few minutes early and enjoy your Thanksgiving break. And when we come back, we'll basically be looking at all of the little piles of rubble that are hanging around, all the little things. And then maybe by the end of this, we can come up, well, hopefully you guys can come up with your own stories of how this goes, but we'll compare and contrast some of the ideas at the very end of the course. Otherwise, guys, there's no assignment, no video assignment. There's no more video assignments, actually, other than the final project. Do consider doing the creativity project if your grade is suffering in any way. I always love to see what you guys come up with anyways, so that's fun for me. But yeah, have a great break, and I'll see you guys next week.